In this video, we're going to talk about electric potential and electric potential energy. But let's begin our discussion with this. What is electric potential? Electric potential is defined as potential energy divided by charge. In some physics textbooks, you'll see capital U represented as potential energy. Now, there are different types of potential energy that you need to be familiar with. There is elastic potential energy, that is the energy stored in springs. There's gravitational potential energy, which occurs anytime an object is above ground, which it has the ability to fall. And then there's electric potential energy, which is what we're going to talk about. So if I use PE or U in this particular video, I'm using it with reference to electric potential energy. So V is electric potential. PE, electric potential energy. Make sure you notice the difference between them. They sound similar, but they're different. Electric potential is measured in volts. 1 volt is equal to 1 joule of potential energy per 1 coulomb of charge. So an electric potential of 5 volts means that a 1 coulomb charge has 5 joules of potential energy. An electric potential of 12 volts means that a 1 coulomb charge have 12 joules of potential energy with respect to some reference point, of course. Or you could say that 2 coulombs of charge has 24 joules of potential energy. So electric potential is simply the ratio of electric potential energy per unit charge. So now that we've defined electric potential as potential energy per unit charge, let's relate it to something more familiar, that is voltage. Voltage is electric potential difference. Voltage is the change in electric potential. By the way, you may want to take down these notes if you have a piece of paper and a pen with you, or a sheet of paper rather. So voltage would be the difference between the potential at B and the potential at A. So you can write it this way. So if you were to see VBA, that means VB minus VA. If you were to see VAB, that means the difference in the potential at A minus the potential at B. So let's say we have a resistor. A resistor is an electronic component that is used to basically control the flow of electric current in a metal or in a circuit. Now let's say we have 2 points of interest across this resistor. We'll call this point A and point B. Actually, let's make this B. Sometimes my computer acts up. Let's do it that way. Let's say B is at 80 volts, A is at 20 volts. The change in V is 80 minus 20, that's 60. The 80 volts represents the electric potential at B. 20 volts is the electric potential at A. So this is VB and this is VA. This is the voltage. Voltage is electric potential difference. It is the difference in the electric potential between 2 points. So hopefully this helps you to see the connection between voltage and electric potential. The electric potential at B is 80 volts. The electric potential at A is 20 volts. But the voltage across the resistor is 60 volts. So we could say VBA, which is the electric potential at B, minus A, 80 minus 20, that's 60. Or we could say VAB, 20 minus 80, that's going to be negative 60. So let's use another example to help you see the difference between voltage and electric potential. So let's call this B and let's call this A. So let's say for B, this is at 90 volts, and A, it's at negative 30 volts. The electric potential at A is negative 30 volts. The electric potential at B is 90 volts. So what is the voltage across the resistor? Go ahead and calculate VBA and VAB. So to calculate VBA, it's going to be the final value, VB, minus the initial value, A. So we're going from, when you think of this, we're going from A to B, initial to final. So that's 90 minus negative 30. So that's positive 120. So VBA is positive 120. Now if we want to calculate VAB, in analyzing the direction, we're going from B to A. So B becomes the initial value, A becomes the final value. So it's final, VA, minus initial. So A, VA is negative 30, minus VB, which is positive 90. So we get negative 120. So let's think about what's happening here in terms of the direction in which we're moving. So during the first part, we're going from A to B. Is the potential increasing or decreasing? As we go from A to B, it changed from negative 30 to 90. So the potential is increasing. Therefore, we got a positive value. Now for the second part, we went from B to A, from a high potential to a low potential. So the potential is decreasing, thus we can see why the change is negative. So I wanted to help you to understand the reasoning behind these two formulas, so that if you understand what they mean, you'll remember how to write them correctly. Now let's talk about how we can calculate the work done when a charge moves through a certain voltage. Let's say that the direction of motion is from point A to point B. So the voltage, which in this case is going to be VBA, that is the potential at B minus the potential at A. And if you recall, electric potential is equal to the electric potential energy divided by the charge. So VB is going to be the potential energy at B divided by the charge. VA is going to be the potential energy at A divided by the charge. Now I'm going to factor out 1 over Q. Doing so, I will get the potential energy of B minus the potential energy at A. Or we could say the change in potential energy. So we have 1 over Q times the change in potential energy going from A to B. Now some other formulas that you need to be familiar with are these. Work is equal to the positive change of kinetic energy, but the negative change of potential energy. In a system where energy is conserved, as kinetic energy increases, the potential energy decreases. Think of a ball that's fallen down. As it falls from a certain height, its potential energy decreases, but it's speeding up as it approaches the ground, so the kinetic energy goes up. This is true when the only forces acting on the system are conservative forces. That's when mechanical energy will be conserved. If there are non-conservative forces acting on the object, then this may not apply. So just something to keep in mind. But what we need to take from this is that work is equal to the negative change of potential energy. So therefore, the change in potential energy is equal to negative W. So we have 1 over Q times negative W, which we can write as negative W over Q. And that equals delta V. So if delta V is equal to negative W over Q, we can multiply both sides by negative Q to get an expression for W. So the work done by a charge or on a charge as it moves through a certain voltage is this equation. It's negative Q delta V. Now let's work on this example problem. How much work is required to move a negative 500 microcoulomb charge across a potential difference of 300 volts? For this problem, all we need to do is use this formula. The work is going to be negative Q times delta V. So we have the charge. Q is negative 500 microcoulombs, or 500 times 10 to negative 6 coulombs. The voltage, or the change in V, that's the potential difference across 2 points. So that's positive 300. Now recall, 1 volt is 1 joule per 1 coulomb. Let me write that better. So it's 1 joule over 1 coulomb. So we can write this as joules per coulomb. So thus the unit coulombs will cancel, and we're going to get the work in joules. So we have two negative signs, which will make this positive. So it's going to be 500 times 10 to negative 6 times 300. And the work done is going to be 0.15 joules. So that's how much work is required to move this particular negative charge across a potential difference of 300 volts. Number 2, 100 joules of work was done by an electric field on a 5 coulomb charge. I forgot to put the word charge, to accelerate it from point A to point B. What is the voltage across points A and B? So let's draw a picture. So let's call this point A, and we're going to call this point B. So we're going to move a charge from point A to point B. And this is a positive charge. So if it takes 100 joules of work to move this 5 coulomb charge from A to B, what's the voltage across it? So we could use this formula to get the voltage. To solve for V, it's going to be the work divided by the charge is equal to delta V. Now the work is 100 joules. The charge is 5 coulombs. I wouldn't really worry about the negative sign too much. I would focus more on direction, but we'll talk more about that. If you were to plug in the negative sign, you'll just get a negative answer. So 100 divided by negative 5 is negative 20. You could simply say the voltage across points A and B is 20 volts. Now here's a question for you. If the electric potential at point A is 50 volts, what is the electric potential at point B? Now we know the difference is 20. The question is it 20 volts higher or 20 volts lower? Would you say if we add 20 to 50, that would be 70. If we subtracted 50 by 20, it would be 30. We know the difference is 20, but which of these two values will be correct? Now looking at this is saying that the voltage is negative 20. That's an indication that B should be 20 volts less than A, which will indicate that 30 volts is the answer. But let's confirm it though. Let's say we have two parallel metal plates. Let's say the first one has a positive charge and the second one has a negative charge. Now the electric field is going to go from the positively charged plate to the negatively charged plate. Now let's say that at the negatively charged plate, the electric potential is 0. The electric potential at the positive plate is going to be higher. It could be 100 volts. Now what's going to happen if we put a positive charge here? Will it move to the negative plate or the positive plate? A positive charge will feel a force that will accelerate it in the same direction as the electric field. So in this case, it's going to be attracted to the negatively charged plate. So notice the direction in which the positive charge moves. The electric field causes the positive charge to move from a high potential to a low potential. Now, if there was a negative charge, the electric field rather, would cause the negative charge to move from a low potential to a high potential. Now, it's important that you understand that. So I'm just going to summarize this for notes. So for a positive charge, it's going to move from a high potential or high V to a low V. It will accelerate in that direction due to electric field. But a negative charge will accelerate from a low V to a high potential due to electric field. Now, in this problem, the electric field is accelerating the positive charge from point A to point B. And we know that an electric field will accelerate a positive charge from high potential to low potential. So if the 50 volts is considered the high potential, the low potential must be 30. If it was 70, it will be going from low to high and not high to low. So conceptually, that's how you can determine that this is indeed the correct answer. And of course, if you use the fact that the voltage change is -20, that helps you to see that it's going from high to low as well. But in the event that you didn't take the negative sign into an account, just understanding this concept will help you to see that the positive charge is going to move towards a lower voltage. So conceptually, you would know that you need to subtract 20 and not add 20 to get the answer. If we were dealing with a negative charge, we would add 20. The negative charge will go from a low potential to a high potential, but the positive charge will go from a high potential to a low potential when accelerated by an electric field. Number 3. A positive charge is released from rest at point A as shown in the figure below. As it accelerates toward point B, is the charged electric potential energy increasing or decreasing? What would you say? Well, we know that there's going to be an electric field that will emanate from the positively charged plate, and it's directed towards the negatively charged plate. Now, we also know that the charge is going to feel a force that will accelerate it in the same direction as the electric field. So it's going to accelerate towards point B and then towards point C. Now, how can we describe what's happening with regard to the charge's potential energy? Well, since there's a force that's accelerating the charge towards point B, there must be an acceleration. Based on Newton's second law, the net force is equal to ma. So if there's a force, there's an acceleration. Now, what's happening to the speed of the charged particle if it's accelerating? It's accelerating towards the right. Its velocity is increasing, and therefore the magnitude of the speed is going to increase as well. So v is increasing for this particular particle. If the speed is increasing, what's going to happen to the kinetic energy? Which basically answers part B. As the speed increases, the kinetic energy of this positive charge is going to go up, which means that the change in kinetic energy is positive. Now, if the kinetic energy increases, what's going to happen to the potential energy? As the kinetic energy goes up, the potential energy goes down. We don't have any non-conservative forces acting on a positive charge. The only force acting on it is the electric force due to the electric field, which is a conservative force like gravity. So therefore, the mechanical energy of the positive charge will remain constant. The mechanical energy is the sum of the kinetic energy and the potential energy. So if the mechanical energy is constant due to the lack of any non-conservative forces acting on the charge, as Ke goes up, Pe must go down. So since the potential energy decreases, the change in the potential energy will be negative. Now, what about part C? Is the work done on this particular charge, is it positive or negative? Work is equal to the change in kinetic energy. So if the change in kinetic energy is positive, the work done on its positive charge is also going to be positive. Now let's get rid of this. There's another way in which we can analyze the work done, if it's positive or negative. Keep in mind, work is force times displacement. If the force vector and the displacement vector are in the same direction, the work done is going to be positive. If the force vector and the displacement vector are in opposite directions, the work done is negative. Now, if the force vector is perpendicular to the displacement vector, so if they're at right angles, then the work done is 0. So let's use this to confirm our answer. In this example, the charge feels a force that's accelerating it towards the right. So that's the force vector. It's heading due east. Now what about the displacement vector? Where's the charge moving? Is it moving to the left or to the right? Well, we know it's going to move towards the negatively charged plate in the direction of the electric field. So the displacement vector for this charge is towards the right. Because the force and the displacement vector are in the same direction, the work done on that charge is positive. Its kinetic energy will increase. Now for part D, we're going to repeat parts A through C. So the new situation is that the positive charge is going to start at point B. So it's at point B, and at this instant, it's moving to the left. So going back to part A, actually let's do part B first. Is the kinetic energy increasing or decreasing? So let's think about what's happening here. The charge is moving towards point A. However, the electric field is still towards the right. So therefore, it's still going to feel an electric force towards the right. So what does it mean when F and V are opposite in direction? Let's talk about that. When the force vector and the velocity vector are in the same direction, this means that the object is accelerating. It's speeding up. The force vector and the acceleration vector are in the same direction. So think of F and A as being similar. Now, if the force vector and the velocity vector are opposite to each other, the object is slowing down. It's decelerating towards the left. It's accelerating towards the right if you look at just the positive sign, but the signs of acceleration and velocity are different. Therefore, it's going to be slowing down. So make sure you understand that. If the force and velocity vectors are in the same direction, the object is going to be speeding up. If they're in opposite directions, the object is slowing down. And then if the force and velocity vectors are perpendicular to each other, the object is neither speeding up or slowing down, but it's going to turn. And it's going to do so at constant speed, which means that we're going to have circular motion. Now in this example, the force and the velocity vectors are opposite to each other, which means it's going to be slowing down. The speed is going to be decreasing. If it's slowing down, that means that the kinetic energy is decreasing. Therefore, the change in kinetic energy is negative now. If the kinetic energy is decreasing, that means that the potential energy, the electric potential energy, is increasing. So the change in electric potential energy is going to be positive. Now what about the work done? Since the change in kinetic energy is negative, the work done on this particle, or on this positive charge, is going to be negative as well. Because this force, it's not accelerating the charge, it's slowing it down. It's decreasing its kinetic energy. And therefore, because the electric force is decreasing the kinetic energy of the charge, we could say that it's doing negative work on it. It's slowing it down, not speeding it up. Now, let's look at force and displacement. For the positive charge, the force vector is due east. But because the velocity vector is due west, that means that it's moving to the left. So it's going to have a displacement in the negative x direction, at least for a time, until it changes direction. But while it's moving to the left, the displacement vector is directed to the left. Whenever the force and displacement vectors are opposite to each other, we can see that the work done is going to be negative. Therefore, the electric field is not speeding up the particle, it's slowing it down. It's doing negative work on it. Number 4. How much work is required to move a negative 50 microcoulomb charge from an electric potential of negative 50 volts to 250 volts? Let's call this point A, point B. So this time the electric field vector is going to be pointing towards the left, away from the positive charge towards the negatively charged plate. Now, the positively charged plate is going to have a higher potential. It's going to be at an electric potential of 250. The negatively charged plate, it makes sense that it's going to be at a lower potential, or an electric potential of negative 50. The voltage between these two is the difference of those two numbers. But before we calculate voltage, let's write the equation for work. Work is going to be negative Q times the voltage. Now the charge, the negative charge, is going to feel a force that will accelerate it in the direction opposite to the electric field. It's going to accelerate towards the positively charged plate. So the negative charge is going from A to B. So B is the final position, A is the initial position. So if it's going from A to B, the change in voltage, or the sign of delta V, will it be positive or negative? The negative charge is going from a low potential to a high potential. So because the potential is increasing, the voltage should have a positive sign. So it's being accelerated across a positive voltage. Delta V is going to be VB minus VA. So the final potential that it experiences is 250. The initial potential is negative 50. So 250 minus negative 50, that's 250 plus 50, so that's 300. So we have a negatively charged particle with a charge of negative 50 microcoulombs, and it's accelerating through a potential difference of positive 300 volts. So remember, an electric field will accelerate a negatively charged particle from a low potential to a high potential. However, an electric field will accelerate a positive charge from a high potential to a low potential. So if we had a positive charge, it will go towards the low potential plate, or negative 50. But since we're dealing with a negative charge, it's going to go from low V to high V. Now these two negative signs will cancel. So to get our answer, it's going to be 50 times 10 to the negative 6 times 300. And so the work is going to be 0.015 joules. Now the answer is positive. The question is, does the sign of the work make sense? The work done on this negative charge, should it be positive or negative? Well, since we got a positive answer from the formula, chances are this is correct. But let's analyze it. In what direction is the electron moving? From left to right or right to left? We know that it's going from A to B, from a low potential to a high potential. So therefore, the displacement vector is towards B because it's moving in that direction. Now, because the force and the displacement vector are parallel to each other, they're in the same direction, the work done by the electric field on the negative charge is positive. These two vectors are parallel to each other in the same direction. Now let's analyze it from the other angle. We know that this charge is accelerating towards the right, therefore it's speeding up. If the speed is increasing, the kinetic energy is increasing, which means the change in kinetic energy is positive. Therefore, the work done on that charge is positive as well. We could say that the electric field does positive work on the negative charge because it's increasing its kinetic energy. It's making it move faster. So now let's move on to the next part, part B. If the charge accelerates from rest, what is the final speed if it has a mass of 0.01 kilograms? 0.01 grams. Now we know that work is equal to the change in kinetic energy. And the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Kinetic energy depends on the speed. There is no kinetic energy if a particle or an object is not moving. So notice that it accelerates from rest. Therefore, the initial speed is 0, which means that the initial kinetic energy is 0. So if this is 0, we could say that the work is equal to the final kinetic energy. So let's go ahead and use that formula. So for this particular example, because it accelerates from rest, work is equal to the final kinetic energy. And the final kinetic energy is 1/2 mv squared. So the work is 0.015 joules. And then the mass is 0.01 grams, but we need to convert that to kilograms. To convert grams to kilograms, here's what you can do. Keep in mind there's 1,000 grams per 1 kilogram. So you need to divide. 0.01 divided by 1,000 is 1 times 10 to the negative 5 kilograms, which is 0.00001. So now let's solve for V. If we take 0.015 divided by 0.5 and then take that result divided by 1 times 10 to the negative 5, you'll get that 3,000 is equal to V squared. Now let's take the square root of both sides. The square root of 3,000 is 54.77. So this is going to be the final speed of the negative charge as it accelerates from an electric potential of -50 to 250. Number 5. A 300 volt battery is connected across two parallel plates that are separated by a distance of 50 centimeters. What is the magnitude of the electric field? So this is the electrical symbol of a battery. The long side is the positive side. The short side is the negative side. And this battery has a voltage of 300 volts. Let's see if I could put that somewhere else where there's more space. The electric field is going to emanate away from the positive plate toward the negative plate. How can we calculate the magnitude of the electric field? Well, let's write down some formulas. We know that work is equal to -Q delta V. And work is also equal to force times displacement. So therefore, we can set these two equal to each other. So the force times the displacement is equal to the charge times the voltage. Now the electric force that's acting on a charged particle in an electric field is going to be the electric field times that charge. So let's replace F with what we have here, E times Q. So we have E times Q times D is equal to -Q delta V. So dividing both sides by Q, we can cancel that term. And then dividing both sides by D, we get this equation. The electric field is equal to negative the change in voltage divided by the distance. So that's the formula that we need to use in order to get the answer. So the electric field is going to be the voltage, which is 300, divided by the distance. The distance is 50 centimeters. To convert centimeters to meters, divide by 100. So that's going to be 0.5 meters. 300 divided by 0.5 is 600. So we're looking for the magnitude of the electric field. Therefore, we can ignore the negative sign. So we can say that the electric field has a magnitude of 600 volts per meter. V is in volts, D is in meters. So this is one way in which we can express the electric field. We could also say that the electric field has a magnitude of 600 newtons per coulomb. Because remember, electric field is also force over charge. Force is in newtons, charge is in coulombs. So there's two units that you could use to describe electric field. You could say it's newtons per coulomb or volts per meter. So if we analyze this form of the electric field with the units volts per meter, it tells us how the electric potential changes over distance. That means that every time the distance changes by 1 meter, the electric potential will change by 600 volts. If the distance changes by 2 meters, the electric potential will change by 1200 volts, provided, of course, these two are far apart for us to move by 2 meters. If we were to move a distance of half a meter, the electric potential will change by half of 600 or 300. So that's what it tells us. It tells us how the electric potential changes over distance. Now you might be wondering, what is the purpose of the negative sign? The purpose is to indicate direction, which for most cases, you really don't have to worry about it in this particular problem. But for those of you who want to understand how it works, here's what you can do. So this distance, or d value, came from this equation. Work is equal to force times displacement. So technically, this is displacement. That is the displacement of the charged particle. So let's say we have a negatively charged particle near the bottom of the plate. This charged particle will feel a force that will accelerate it towards the positively charged plate. So therefore, if it's moving in the upward direction, we could say that the displacement is positive. So as it moves from, let's say, point A to point B, it has a displacement of positive 0.5 meters. Now let's say that the electric potential of the plate at the bottom is assigned a value of 0 volts. Therefore, the electric potential of the plate on top, that is the positively charged plate, is going to be 300 volts because it's connected across a 300 volt battery. Therefore, the potential difference, or the voltage across those two plates, must be 300. Now, since I'm running out of space, I'm going to use this equation here. So as we move in the direction of the displacement vector from point A to point B, delta V is going to be positive because we're moving in the direction of higher potential. So we can say the final potential is 300 minus the initial potential of 0 divided by a positive displacement of 0.5 meters, and this is the unit V. We're going to get negative 600 volts per meter. Now the negative sign tells you the direction of the electric field. The electric field is going to emanate from the positively charged plate to the negatively charged plate. And notice that it's going in the negative y direction. So along the vertical axis, the negative sign tells us that it's going in a negative y direction. So that's what the sign can tell you. It tells you the direction of the electric field. But you really don't need to worry about that, because if you know the signs of the plate, you could easily determine the direction of the electric field. So you could ignore this negative sign and apply the and then apply the direction based on the signs of that plate. But that's how it works for those of you who are interested. So now let's move on to the second part of this problem. So the magnitude of the electric field is 600 volts per meter. Remember, if you're looking for the magnitude, make the answer positive. What about calculating the electric potential at the following distances from the negatively charged plate? First, I need to create additional space. So I'm going to put the potentials here. So relative to the negatively charged plate, let's assign this a value of 0 centimeters, and this is going to be 50 centimeters. So at 0 centimeters, the potential is 0 volts. At 50 centimeters, we can see that it's 300. What is the potential at, let's say, 25 centimeters? At 25 centimeters, it's simply going to be half of 300. You can see that conceptually. So it's going to be 150 volts. That means anywhere along this horizontal line, the potential is 150 volts between those two plates. Now, what is the electric potential, let's say, at 10 centimeters above the negatively charged plate? You can also do this conceptually. If 50 centimeters corresponds to 300, what does 10 centimeters correspond to? Going from 50 to 10, we'll need to divide by 5. So going from 300 to the number that should be there, we'll need to divide by 5 as well. 300 divided by 5 gives you 60 volts. Now what about the potential at 40 centimeters? To get that answer, you could simply go from 10 to 40, which means you need to multiply by 4. So going from 60 to that point, multiply by 4 as well. 60 times 4 is 240. So that's one way in which you can do it conceptually. There's another formula that you could use too. Let's get the electric field in volts per centimeter as opposed to volts per meter. So E is going to be V over D. The voltage is 300. And we're going to divide it by 50 centimeters. So we can cross out a 0. This becomes 30 over 5. So we get the electric field as being 6 volts per centimeter. So we could say it's 600 volts per meter or 6 volts per centimeter. So remember earlier we said that the electric field in this form tells us how the electric potential changes over distance. 6 volts per centimeter tells us that as we move 1 centimeter away from the negatively charged plate, the potential will increase by 6 volts. So what if we move a distance of 10 centimeters? Well, it's going to increase by 60 volts. So at 10 centimeters, we have a potential of 60 volts. At 20 centimeters, it's going to be 120. At 30 centimeters, it's 180. At 40, it's 240. And at 50, it's 300. So every time we move 10 centimeters away from the negatively charged plate, in this example, the potential is increasing by 60 volts. So that's what this tells us. 6 volts per centimeter or 60 volts per 10 centimeters. Now, if the electric field is the voltage divided by the distance between the plates, we could say that V is equal to ED if we multiply both sides by D. So in this case, this V is not going to be voltage, but it's going to be electric potential. So we could say that the electric potential V is equal to the electric field times the distance from the negatively charged plate. So let's say we want to calculate this value using this number that we have here. So the electric field is 6 volts per centimeter. If we multiply this by 25 centimeters, the unit centimeters will cancel, and 6 times 25 will give us 150. The value of 6 quarters is $1.50. So we get a potential of 150 volts, which we have here. So we could use this formula to calculate the electric potential at any point of interest. So we can get it at 15 centimeters. It's going to be 6 volts per centimeter times 15 centimeters. And so these two will cancel. 6 times 15 is 90. So at 15 centimeters, the potential is 90 volts with respect to the negatively charged plate. Well, I would say the voltage is 90 volts with respect to the negatively charged plate. The potential is just 90. Now let's focus on part E, where it's 35 centimeters. So let's do this two ways. If we add 25 plus 10, that will give us 35. So therefore we can add 60 plus 150, and that will give us the potential at 35 centimeters. And so that's going to be 60 plus 150 is 210. And we can confirm it with this formula. So if we multiply this by 35 centimeters, 6 times 35 is 210. So anywhere along this line, the electric potential between the two charged plates is 210 volts. So that's how you can calculate the electric potential anywhere between the two plates. It's by using this formula. Number 6. 500 volts is applied across two parallel plates separated by a distance of 4 millimeters. Part A. What is the magnitude of the electric field? So the electric field is going to move away from the positive plate and it's going to point towards the negative plate. And these two are separated by a distance of 4 millimeters. So to calculate the electric field, it's going to be negative delta V over D. So let's analyze that. Let's say this is point A and this is point B. The positive charge will feel a force that will accelerate it from rest to the negatively charged plate. So its displacement vector is going to be towards the right because it's going to be moving in that direction. Now the voltage is 500. So let's assign a value of 0 to the negatively charged plate, which means that the positively charged plate will have an electric potential of 500. So as we move from point A to point B, we're going from a high potential to a low potential. So the potential is decreasing, therefore the change in potential should be negative. So as we move from point A to point B, we're moving from an initial position to the final position. So the final potential is 0 volts minus an initial potential of positive 500 volts. And our displacement as we move from left to right, because we're moving in the positive x direction, the displacement is going to be positive 4 millimeters. To convert millimeters into meters, divide by 1,000. 4 divided by 1,000 is 0.004. Now these two negative signs will cancel. But first, let's do it this way. This is going to be negative. 0 minus 500 is negative 500 over 0.004. So we can see that delta V is negative because we're moving from a high potential to a low potential. So the potential is decreasing as we go from A to B, so the change in potential is negative. So that's why we got that negative value here. So two negatives will make a positive, and this makes sense because the electric field is pointing in a positive x direction. So this equation should give us a positive answer. 500 divided by 0.004 gives us an electric field value of 125,000. Now we could say volts per meter, or we could say newtons per coulomb. I'm going to use newtons per coulomb because that's going to lead us into part B. For part B, what is the magnitude of the electric force that will be exerted on a positive 200 microcoulomb charge? the electric force is equal to the electric field times the charge. So we have an electric field of 125,000 newtons per coulomb, and we're going to multiply that by a charge of 200 microcoulombs, or 200 times 10 to the negative 6 coulombs. So we can see here that the unit coulombs will cancel, and we're going to get the force in newtons. So multiplying those two numbers gives us a force of 25 newtons. So that's the answer for part B. Now let's move on to part C. Calculate the acceleration and final speed of the 0.1 gram charge as it moves from rest toward the negatively charged plate. So according to Newton's second law, we know that the net force is equal to mass times acceleration. The only force that we have in the x direction is the electric force. So the electric force is going to be equal to the net force in the x direction. So the acceleration is going to be the electric force divided by the mass. The electric force is 25 newtons. The mass is 0.1 grams. To convert that to kilograms, divide by 1,000. 0.1 divided by 1,000 is 0.0001. So 25 divided by that number gives us an acceleration of 250,000 meters per second squared. So now we could use this to calculate the final speed. We can use v final squared is equal to v initial squared plus 2ad. We know the initial speed is 0. It moved from rest from the first plate. We have the acceleration, which is 250,000, and we have the displacement. It's 4 millimeters, or 0.004 meters. 2 times 250,000 times 0.004, that's 2,000. So now we could take the square root of both sides. The square root of 2,000 is 44.72. So the final speed is going to be 44.72 meters per second. Now here's another way in which you can get the answer. Keep in mind the work is equal to the change in kinetic energy. It's equal to the final kinetic energy minus the initial kinetic energy. And since the charged particle is accelerating from rest, there is no initial kinetic energy. That's going to be 0. Now the work is equal to negative q delta v. So that's the work done on a charge when you accelerate it through a potential difference or voltage. Kinetic energy is 1/2 mv squared. So you have to make a distinction between these two v's. So I'm going to try to make voltage like a big V and speed a small v. So let's isolate the speed. Let's multiply both sides by 2 first. So we can get rid of this, and let's divide by m. So we have negative 2q delta v over m is equal to v squared. Taking the square root of both sides, we get that the speed is equal to the square root of negative 2q delta v over m. Now, if you make everything positive and ignore the negative sign, you're going to get the magnitude of the speed, which will still be correct in this problem. But if you want to incorporate the negative sign, here's what you can do. So it's negative 2. We have a positive charge of 200 times 10 to the negative 6. Now remember, as we move from point A to point B, we're going from a high potential to a low potential. So from 500 to 0, the potential is decreasing. So the change of potential is negative 500 volts. So this negative sign is going to counteract this other negative sign. And then we're going to divide it by m, which is the mass, and that's 0.0001 kilograms. So go ahead and plug that in. So this will give you the same answer, 44.72 meters per second. So this is a quick and simple formula that can help you to calculate the final speed if you know the magnitude of the charge, the potential difference in which the charge is being accelerated, or the voltage, and the mass of the charge. Number 7. What is the speed of a 500 eV electron? So you might be wondering, what does this stand for? EV stands for electron volt. Now you might be thinking EV represents voltage, but it's a little different than that, because voltage is measured in volts, but the electron volt is actually a unit of energy, much in the same way that the unit joule is a unit of energy. Now, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So this is the energy that an electron will acquire if it is accelerated through a potential difference of 1 volt. So let me just give you a visual picture here. So let's say that this is a negatively charged plate, and this is the positively charged plate. And let's say the potential of this plate is 0, and this one is 1. So the potential difference is 1 volt. As this electron accelerates from the negatively charged plate to the positively charged plate, its kinetic energy is going to increase. And that 1 electron will acquire 1.6 times 10 to the negative 19 joules of kinetic energy. At the same time, it's going to lose 1.6 times 10 to the negative 19 joules of potential energy. So that's the change in energy that the electron either acquires or loses, depending on which energy you're talking about, when it is accelerated through a potential difference of 1 volt. Now keep in mind, 1 volt is 1 joule per 1 coulomb. So using this equation, W is equal to negative Q delta V. The charge of an electron is negative 1.602 times 10 to the negative 19. And when it moves through a potential difference of 1 volt, as it goes from low potential to high potential, so delta V is positive. And let me, instead of writing 1 volt, I'm going to write 1 joule per coulomb. So you can see that the unit coulombs will cancel. And so the work done on that electron is positive 1.602 times 10 to the negative 19 joules. So that's how much kinetic energy the electron acquires when it is accelerated through a potential difference of 1 volt. So make sure you know this conversion. Now this energy represents the kinetic energy of an electron. So the formula that we're going to use is this equation to get the speed of an electron. But we need to convert this to joules. But let's isolate V in this equation. So I'm going to multiply both sides by 2 and divide by m. So on the right, 1/2 and 2 will cancel, and m will cancel as well. And then I'm going to take the square root of both sides. So the speed is going to be 2 times the kinetic energy in joules divided by the mass in kilograms. So to convert 500 electron volts into joules, it's going to be 1 electron volt on the bottom times 1.602 times 10 to the negative 19 joules. And then EV will cancel. So the kinetic energy of the electron is 8.01 times 10 to the negative 17 joules. So now we could plug that into this equation. So the speed of this electron is going to be 2 times the kinetic energy divided by the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. So the answer that you should get is 1.326 times 10 to the 7 meters per second. So that's how fast a 500 electron volt electron is moving. Now let's move on to part B. So first, let's start with 27 mega electron volts. Let's convert that to electron volts. Mega is 10 to the 6. So 1 mega electron volt is 1 times 10 to the 6 electron volts. A kilo electron volt is 1,000 electron volts. And then let's convert this to joules. So we can cross out the unit mega electron volts and the unit electron volts. So it's 27 times 1 times 10 to the 6 times 1.602 times 10 to the negative 19. And so you should get 4.3254 times 10 to the negative 12 joules. Now let's calculate the speed. And let's divide this by the mass of the electron. The answer that I got is 3.08 times 10 to the 9 meters per second, which I think is a little bit too fast for an electron. But nevertheless, that's the process that you would use to get the answer though. Number 8, calculate the electric potential generated by a 93.3 nanocoulomb charge at a distance of 1 meter and 8 meters from the charge. So let's draw a picture. Let's start with a positive charge. And at a distance of 1 meter, we want to calculate the electric potential that it generates. And also at a distance of 8 meters. So what I'm going to do is I'm going to put this charge at the origin. So let's say this is a distance of 1 meter. To calculate the electric potential generated by a point charge, it's equal to kq over r, where r is the distance between a charge and a point of interest. So if we call this point A, we could say that this is the electric potential at point A. K is 9 times 10 to the 9. Q is 93.3 times 10 to the negative 9 coulombs. And R is 1. So if we multiply these numbers, it will give us 839.7 volts. Now let's round that to 840. So at 1 meter, it's approximately 840 volts. So that is the electric potential at a distance of 1 meter from this particular charge. Now the electric potential can be a positive value or a negative value. Since Q is positive, the potential that it creates will be a positive value too. By the way, electric potential is scalar, so you can add them without worrying about direction. So a negative charge will generate a negative electric potential. So now let's use this equation again to calculate the electric potential at a distance of 8 meters from the charge. So everything is going to be the same except our R value. We're going to divide it by 8 instead of by 1. So the electric potential will be approximately 105 volts. So let's say 8 meters is here. So it's 105 volts at that point. So notice that R is on the bottom of the equation. So as we increase the distance, the electric potential created by a point charge decreases. And it's not R squared, it's R to the first power, which means as we double the distance, the electric potential will reduce by a factor of 1/2. Or it will be reduced by a factor of 2, or it will be 1/2 of its original value. So if we double the distance from 1 meter to 2 meters, the electric potential at 2 meters will be half of what it was at 1 meter. So half of 840 is 420. If we double the distance from 2 to 4, this is going to cut in half. It's going to be 210 volts. And then if we double the distance from 4 to 8, this will be 1/2 of its original value. 1/2 of 210 is 105. By the way, if you want to get this answer, simply take this number divided by 4. 840 divided by 4 is 210. Since this is 1 meter, we could use this value to easily calculate the other values. So let's say if we want to find the electric potential at 3 meters, we just got to take 840 divided by 3. So it's going to be 280 volts. If we wish to calculate it at 6 meters, we can going from 3 to 6, the distance is doubled, so we need to divide the potential by 2. So half of 280 is 140. And then you can add more values if you want. But notice the general theme here. As we move away from the charge, the potential decreases. Let's say if we want to get it at 7 meters, it will be 840 divided by 7. So it's going to be 120 at 7 meters. So notice that as we move from 1 meter to 2 meters, the change in electric potential is 420 volts. That's how much it decreases by. But as we move from 7 to 8, the change is only negative 15 volts. So as you begin to move further and further away from the charge, the change in electric potential it's going to become smaller and smaller. If you were to plot the electric potential and R, the distance between a point of interest and the charge, you would get a graph that looks like this. So as you can see, the electric potential is very high when you're very close to the charge. But as you begin to move away, it decreases slowly and slowly. As we can see here, going from 7 to 8, the decrease was only 15. But going from 1 to 2, the decrease was huge, 420. So the electric potential is very high when you're very close to the charge, but it's very low when you're further away from it. Now let's move on to part B. What is the electric potential produced by a negative 50 microcoulomb charge at a distance of 30 centimeters? So let's draw our negative charge. And let's call this point A. So let's calculate the electric potential at point A. So it's going to be K times Q over R. Now Q is a negative value. It's negative 50 times 10 to the negative 6 coulombs. And we're going to divide that by R. The distance between the point of interest and a charge is 30 centimeters, which is 0.30 meters. Electric potential is a scalar quantity. It could be positive or negative, but direction is not important for electric potential. You won't say 50 volts east. It doesn't apply. So we get this. Negative 1.5 or negative 1.5 million volts. Or we could say negative 1.5 times 10 to the 6 volts, which is negative 1.5 megavolts. So that's the electric potential at point A. So just remember, positive charges, they create positive electric potentials. Negative charges generate negative electric potentials. Now the next thing that we need to talk about is something called equipotential lines. This first circle here is known as an equipotential line. What does that mean? Well, let's think of the word equipotential. So first we have the word potential, like electric potential measured in volts. And then we have the prefix equi. Think of equivalent. So anywhere along the edge of this circle, the electric potential is equal. So at point D, the electric potential is 300 volts. At point A, it's also 300 volts. At point C, it's 300 volts. Anywhere along that line, the electric potential is equal. It's the same. It doesn't change. So it's called an equipotential line. Now let's understand why that's the case. Electric potential due to a point charge can be calculated using this equation. So with respect to point A or point D, Q still has the same magnitude. So Q doesn't change. K, 9 times 10 to the 9, that's a constant. That doesn't change. And here, what we have here is a circle. The distance between the center of the circle and point A is the radius of the circle. The distance between Q and point C is also the radius of the circle. And the distance between point D and Q, or the center of Q, is also R. So the reason why the electric potential at point A, C, and D are the same is because the distance between those points and the center of the charge is the same. K is the same, Q is the same, and R is the same for each of those points. So anywhere along that circle, the electric potential will be the same. So it's called an equipotential line or surface. For 2D shapes, it's equipotential line. For a 3D shape, an equipotential surface. Now, here's a question for you. Let's say if we were to place a positive charge at point A. Let's say that charge has a magnitude of 100 microcoulombs. What is the work done, or what is the work that's required to move this charge from point A to point C? So let's say if we want to move it along this line from point A to point C, how much work is required to do that? And let's compare it from moving from point A to point B. So how much work is required to move a 100 microcoulomb charge from point A to point C along the circle and from point A to point B? So let's start from point A to point B. To calculate the work, we could use this formula. It's negative Q delta V. So we have a 100 microcoulomb charge, and it's being accelerated through a potential difference of 100. We're going from a high potential to a low potential, so the change in potential is negative. It's 200 minus 300, which is negative 100. So the work going from, let's say, A to B, that's negative 100 times 10 to negative 6 times negative 100. So it's positive 0.01 joules, which sounds pretty small. So that's how much work is required to move it from point A to point B. So it's accelerating as it goes from A to B. the speed is increasing, and so the work done is positive. Now, what is the work done going from, let's say, A to C? Now, here's a question for you. As we go from A to C, what is the change in voltage? The change in voltage is 0. Because at point C, the potential is 300, and at point A, the potential is also 300. So the change in potential is 0, therefore, the work going from A to C is 0. So make sure you understand this. The work required to move a charge along an equipotential line will always be 0, because the change in potential is 0. So this positive charge can freely move around this circle without expending energy. It doesn't require any work for that charge to move from A to C to D. If it wants to go from A to B, work will have to be done on that charge to do so. But going from A to C or to D, it can move there without effort. It doesn't require, no work has to be done on that charge to move from A to C to D. So make sure you understand that. Whenever a charge moves across an equipotential line or equipotential surface, no work is done on that charge. But if it moves from, let's say, A to B, where the potential changes, then there's going to be work done on that charge. Number 9, calculate the electric potential at point P using the figure shown below. So let's call this Q1, Q2, and Q3. To calculate the electric potential at point P, we simply need to add up the electric potential created by each charge at point P. So V1 plus V2 plus V3. So that's going to be K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. Now the good thing about this particular formula is that electric potential is scalar. So we could simply add up V1, V2, and V3, and we don't need to worry about direction or vectors and angles. All we need is to determine the distance between Q1 and point P and the distance between Q3 and point P. So let's find the hypotenuse of this triangle. Using the Pythagorean theorem, we could take the square root of 6 squared plus 8 squared. And this is based on a 3, 4, 5 triangle. If you double it, you get 6, 8, 10. So this is 10 meters. And then to get the other hypotenuse, it's going to be the square root of 8 squared plus 15 squared. So this is the 8, 15, 17 triangle. So this is going to be 17 meters. So V1 is going to be K times Q1. Q1 is positive 1 times 10 to the minus 6 divided by R1. R1 is 6. V2 is going to be K times Q2. This time you need to take into account the negative sign. So you got to plug in negative 2 times 10 to the minus 6 over R, which is 8. Correction, R1 should be 10, not 6. I don't know why I put 6 here. But let's fix that. So this is R1, this is R2, and R3 is 17. Now for V3, it's going to be K times Q3. Q3 is 3 microcoulombs. It's positive. And then R3 is 17. So let's do this one step at a time. Let's get V1 first. That's 9 times 10 to the 9 times 1 times 10 to the negative 6 divided by 10. So V1 is positive 900 volts. The electric potential created by V1 at point P is positive because it comes from a positive charge. V2 is going to be 9 times 10 to the 9 times negative 2 times 10 to the minus 6 divided by 8. So for V2, it's going to be negative 2250 volts because it comes from a negative charge. And for the last one, 9 times 10 to the 9 times 3 times 10 to the negative 6 divided by 17. This is going to be positive 1588.2. So if we add those numbers, the net electric potential at point P is going to be positive 238.2. So that's how you can calculate the electric potential due to multiple point charges. Number 10. A negative 2 microcoulomb charge is 2 meters to the right of a positive 1 microcoulomb charge. At what point along the x-axis relative to the positive charge will the electric potential be equal to 0? So let's begin with a picture. So first, we have a positive charge, which is here. And then to the right of that, we have a negative charge. And they're separated by a distance of 2 meters. Now, somewhere, maybe not the middle, but somewhere along that line, the electric potential will be 0. Now let's call this Q1. We're going to call this Q2. Q1 is positive 1 microcoulomb. Q2 is negative 2 microcoulombs. So it's not going to be 0 at the center because this is bigger. It's going to be negative at the center. So it's going to be closer to the smaller positive charge. So let's call this point P. We're defining point P as the point where the net electric potential is 0. So we want to calculate the distance between point P and the positive charge. So we're going to call that x. If that's x and the total is 2, this segment has to be 2 minus x, because x plus 2 minus x is equal to 2. If we can calculate x, then we can get the distance between the first charge and the point where the electric field will be 0. Now the electric field at point P is going to be the sum of the electric field created by charge 1 and charge 2. Now we want this electric field to be 0. So we get this. I'm going to move V2 to the other side. So negative V2 is going to equal V1. Or V1 is equal to negative V2. Now V1 is K Q1 over R1. V2 is K Q2 over R2. Dividing both sides by K, we can get rid of this. Q1 is 1 microcoulomb. R1 is the distance between Q1 and point P. R2 is the distance between Q2 and point P. So R1 is X. Q2 is negative 2 microcoulombs. And let's see, R2 is 2 minus X. So these two negative signs will cancel. And now what we can do at this point is we can cross multiply. So 1 microcoulomb times 2 minus X, we're going to have this. And then we're going to have X times 2 microcoulombs. So let's divide both sides by 1 microcoulomb. These two will cancel, and on the right side, the unit microcoulombs will cancel. So we'll be left with 2 minus X on the left, and then 2 times X on the right. So now what we need to do is add X to both sides. These cancel. We can bring down to 2, and then 2x plus x, or 2x plus 1x is 3x. Dividing both sides by 3, we get that x is 2 over 3. So 2 over 3 as a decimal, that's 0.6 repeating, or we can round that and say 0.67. So the electric potential will be 0 at point P, where point P is 0.67 meters from the positive charge, or 1.33 meters from the negative charge. So that's it for this problem. That's how you could determine the location where the net electric potential will be 0 between a positive and a negative charge. Consider the electric dipole shown below. A dipole is something that has a positive charge and a negative charge very close to each other. And so this is going to be positive Q and this is negative Q. And they're separated by a distance L. In part A, our goal is to calculate the dipole moment of the electric dipole. The dipole moment is simply the charge times the separation distance. And the charge Q is 10 microcoulombs. So that's 10 times 10 to the minus 6 coulombs. And then the separation distance is 0.01 millimeters. So milli is 10 to the minus 3. So it's 0.01 times 10 to the negative 3 meters. And so let's go ahead and multiply these two numbers. And so the dipole moment for this one is 1 times 10 to the negative 10 coulombs times meters. And so that's how you can calculate the dipole moment of a dipole. It's simply the product of the charge multiplied by the separation distance. Now, how can we calculate the potential at points A, B, C, and D? Now, before we begin, I want you to determine the sign of the electric potential at each of these points. Now, at point A, notice that it's closer to the positive charge than it is to the negative charge. So therefore, the electric potential at point A should be a positive value. Now, point B is still closer to the positive charge. So the electric potential at point B should also be positive. Now, notice that at point C, it's equidistant from both charges. So therefore, the potentials should cancel, and it should be 0 at point C. Now, at point D, it's closer to the negative charge. So the electric potential should be negative at point D. Now, here's the formula that you need to calculate the electric potential. It's going to equal K, where K is 1 over 4 pi times the permittivity of free space, and this is 8.85 times 10 to the negative 12. But K itself is like 9 times 10 to the 9 if you round it. So it's going to be K, which is a constant, times the charge Q, times the separation distance L, multiplied by cosine theta, divided by r squared. Now, cosine is very important because it depends on the angle. Based on the angle, you can be dealing with a point at A or a point at D. So I'm going to show you how to use it for each point. So let's calculate the electric potential at point A. So K is 9 times 10 to the 9. Q is 10 microcoulombs, so that's 10 times 10 to the negative 6. The separation distance is this value, so that's 0.01 times 10 to the minus 3 meters. Now, at point A, relative to the center of this dipole, notice that point A it's at an angle of 0. B is at 45, C is at 90, D is at 180 minus 30 or 150. So the angle for point A, it's on the positive x-axis, so it's 0. This is going to be cosine of 0, then divided by r squared. Now L is very small. This equation works if r is significantly greater than L. And L is like 0.01 times 10 to the minus 3 meters. Compared to 5 meters, 5 meters is significantly larger than 0.01 millimeters. So the distance between point A and the center of the electric dipole is approximately 5 meters. And so that's r. R is the distance between the center and the point of interest. So r is going to be 5 meters in this example. So 9 times 10 to the 9 times 10 times 10 to the minus 6 multiplied by 0.01 times 10 to the minus 3. And cosine 0 is 1 divided by 5 squared. This is going to give us a potential, let's get rid of this stuff, of 0.036 volts. So now let's do the same thing for part B. So K is going to be the same, Q is going to be the same, and L is going to be the same. Now the only thing that's different is the angle. It's 45 degrees, so we need to use cosine 45, and R is different as well, so it's 3 meters. So go ahead and plug that in. And by the way, make sure that your calculator is in degree mode. So the answer that I have is 0.0707 volts. Now the reason why it's higher is because 3 meters is less than 5 meters. So as you move away, notice that the voltage, or the electric potential rather, will decrease. It's inversely related to R squared. So as the distance increases, the electric potential will greatly decrease. And the reason why the values are small is because this negative charge partially cancels the electric potential due to the positive charge. And so that's why the values are close to 0. Now let's use a different variant of the equation for part C. You can still use the same form if you want to. Now recall that we said that the dipole moment is equal to the charge times the separation distance. And so when we multiplied 10 times 10 to the minus 6 by 0.01 times 10 to the minus 3, the dipole moment is 1 times 10 to the negative 10 coulombs times meters. And so what we can do if we want to, we can replace QL with the dipole moment. So this will give us this equation. So V is going to equal K times the dipole multiplied by cosine theta divided by R squared. So it's a lot simpler in this form. However, R still has to be significantly greater than L for this to work. So for part C, it's going to be 9 times 10 to the 9 times the dipole moment, which is 1 times 10 to the negative 10. And then cosine, the angle here, because it's vertical, it's along the y-axis, the angle is 90 degrees, divided by R squared. Now, cosine 90. What is the value of cosine 90? Cosine 90 is equal to 0, so the whole thing is 0. And that's why the angle is so important. And this is the angle relative to the positive charge. So when using this equation, you want to set up the dipole just like this. You want the positive charge to be on the right side, the negative charge to be on the left. Because cosine of anything in quadrant 2, let's say cosine from 90 to 180, or even in quadrant 3, from 180 to 270, will be a negative value. And so you want the negative charge to be in this region, because the value still will be negative, but in quadrants 1 and 4, cosine is positive. And so in order for this formula to work, you need the positive charge to be placed on the right side. So just keep that in mind. Now let's focus on the last part. So let's calculate the electric potential at point D. So it's going to be K times the dipole moment, which is 1 times 10 to the negative 10. Now, the angle relative to the negative x-axis is 30, but this angle is the angle relative to the positive x-axis, or relative to the positive charge. And so the angle measured from the positive x-axis to this point, that is 180 minus 30, or basically 150 degrees. So that's the angle that we need to use, because cosine 150 is a negative value, and so we're going to get a negative potential, as we should expect on the left side. Now the distance between the center and point D is approximately 4 meters. So let's go ahead and plug this in. So this is equal to negative 0.049 volts. And as you can see, it's negative on the left side, but positive on the right side. And so now you know how to calculate the electric potential of a dipole. So make sure you use the appropriate angle in order for this to work.